We're going to hear some message saying that we are live. Well, no messages so far. We're going to hear some message saying that we are live. Well, no messages so far. Okay, we are live. So, boa tarde. Eu gostaria de apresentar a palestra de hoje. Bem-vindos a todos. E nós temos o palestrante, o professor Uri Ascher. O professor Uri Ascher, ele trabalha no Departamento de Ciência da Computação da Universidade de British Columbia, em Vancouver, no Canadá. Ele foi professor titular até 2008 e hoje em dia ele é professor emérito, né? O professor Uri Ascher, ele é bastante reconhecido na área de análise numérica, né? Ele fez a formação universitária dele na Universidade de Tel Aviv, o bacharelado e o mestrado, e o doutorado ele fez na Universidade de Minnesota. O professor Uri Ascher, ele vem muito ao Brasil, ele é bastante conhecido da comunidade científica brasileira, já esteve no INPA várias vezes, inclusive em Florianópolis várias vezes também. E não só conhecido no Brasil, ele é conhecido internacionalmente, ele é, por exemplo, Fellow da Royal Society of Canada desde 2018, e ele é também Science Fellow desde 2010, né? E ele ainda recebeu um prêmio de ciências em 2010 também pela Sociedade Canadense de Matemática Aplicada e Industrial, né? O resumo dele contém muitas outras honrarias e distinções, eu estou citando apenas essas, acho que já está de bom tamanho. É o meu prazer apresentar para vocês hoje o professor Uri, que vai falar sobre Continuous Limits of Discrete Processes. So please, Uri, the floor is yours.
Obrigado, Antônio. Eu vou falar em inglês, porque meu português é fraco. I also wrote a paper on this topic, and you can see the archive number if you are interested. Continuous limits of discrete processes is ancient. This is what Isaac Newton started in a way. Yeah, nothing new there. But in today's computational environment, where you have computers and we compute solutions for anything, it is even more important. Because, first of all, a simple structure that you can analyze better may be obtained. Why, once you get this limit, instead of some sort of a messy discrete structure, you get a continuous differential equations, you can analyze that and obtain phenomenological understanding. Now, in terms of computation, then you can take the continuous limit and discretize it this way. So you start with discrete, go to continuous, then discretize again, but you obtain a method that you can solve more easily and more rapidly, more efficiently. And maybe in some cases, you just forget the original discrete process, and because it starts with the continuous one. And an excellent example of that are the Navier-Stokes equations for governing fluid flow. This is some sort of a nostalgic picture right there nowadays. The Navier-Stokes equations are a continuous model of molecular dynamics in origin, but nobody remembers that. Everybody in computational fluid dynamics starts already with Navier-Stokes equations. Yeah. So big gain there. Much understanding has been obtained by studying Navier-Stokes equations. There are, recently, as I said, there's much more interest in this than before. Here are some instances, there are many more. Artificial time regularization, Professor Antonio is an expert on this, I will not say anything more. Any one-step iterative method, you have iterates x1, x2, xk. In general, you calculate some function g of xk, multiply by step size, alpha k, add xk, and that is your next iterate. Yeah. So now if you take alpha k going to 0, you can think of it as an ODE, first order ODE. If here in this discrete guy, you also have xk minus 1, then it will be a two-step iterative method. Conjugate gradient method is one of those. And then you might look at the second order ODE discretization. In image processing, it is well known to anyone who is doing work in applied inverse problems, for example. People often add a regularization term. And if you start with an image, what does it mean, gradient U here? You look at it as a continuous structure, and then eventually discretize back into the pixels that you have to begin with, or something else. I will not mention more about continuation of nonlinear equations, but there's something called homotopy theory for that. And the second semiconductor equations, there are actually two different, at least two different continuous models for discrete structure that come from also an equation, I think. One of them is, but I will not talk about this, just to mention that. And another one I don't really have time to talk about much is game theory, where there is something called mean field in game theory, and you obtain Hamilton-Jacobi equations this way, starting from a completely discrete game theory. In deep learning, there have been efforts to understand better what network to design based on a differential equation limit. Again, I will not talk much about this. What I want to emphasize here is that you have to be careful with that. A big advantage sometimes can be had, but you also have to concentrate on the given task, what it is that you're tasked to do, and okay, alvo, você tem. And then you have to sort of ensure or be aware of that in the discrete process there may be some interesting properties that maybe are not captured by the continuous one, or more positively to say, make sure that you do have in the continuous limit all the things that you want to see in the discrete. And in particular, it's actually important to distinguish between qualitative understanding that often can be had from a continuous differential equation limit, and quantitative to actually get quantitative information. This is a flock of birds here flying, maybe once seen in a movie or seen it in reality, and it looks like a continuous and chaotic sort of motion for the flock. But so maybe you can describe it in some continuous differential equation way, but to actually assume that you can describe the motion of a particular bird here or here, that is a stretch. The number of birds in such a flock is much smaller than the number of molecules in a glass of water, for example. Okay, so it doesn't follow from the success of fluid flow that everything else is fine. Yeah. I want to, these are all words in the air. So let me just concentrate on several case studies. Okay, here's the list. I will talk about the ones highlighted in blue, and I chose them to be simple, as much as simple as possible, actually. So there's no statistics, no probability theory, no generality in some sense. I wanted to just look at particular tasks and show you what things can be obtained and what surprises may be obtained as well. Okay. So let's start with the first case study, comfort zone, I call it here. I will explain what I mean by this in a minute. There it is. And really, this is a simple thing. If you've had a course in numerical analysis, or even if not, then it's one of the main first tasks to solve a system of linear equations. The matrix A here is symmetric positive definite, and B is a right-hand side given, and you want to find X. And it is well known that these are the necessary and sufficient conditions for an optimum of a minimization of this quadratic function. Okay, f of x quadratic in x. X is a vector. And so we can look at gradient descent for minimization here, and that would be a method for solving ax equal b, okay, as well. And so you calculate the residual, which is minus the gradient in this case, at the point xk, and that will be rk, add alpha times that to xk to get xk plus 1. Okay? So now the goal is to find what is the upper limit for stable choice of alpha. Okay, beyond that limit, I will not be able to obtain a stable solution this way. What is the limit on alpha? So I'm going to use two methods to find that, okay, because it's simple enough. So the first method is to just look at the error, and that will get rid of B, and you get a recursion relationship that says that the error in the kth iterate times identity minus alpha A is the error in the next iterate, and therefore if we take norms, then it is clear that you must have the norm of this matrix bounded by 1, okay, as written here. And that translates immediately to conditions on the eigenvalues of the matrix A, which is positive definite, to recall. And so you come out immediately with this condition. It really takes not more than 5 or 10 minutes to write it down, even if you've never seen it before. So it depends on the maximum eigenvalue of the matrix A. That's first method. No differential equation here. But now here's a second method. We can look at the differential equation dx dt equal to r, the residual that depends on x. Yes. And then apply forward Euler method, and just like we've seen already before, that's going to give you the gradient descent method. Okay, so that's the forward Euler method. Going back, the forward Euler method for the differential equation that I've just shown here. Okay, and so if you happen to know the ODE absolute stability limit, even if you are asleep, which is the case with me, then that you can conclude even more quickly that this is the bound on alpha. Okay, so these are two different methods, and now the question is which one is better, and the answer is it depends on you. You know, for me, this is the faster way of getting there. But for you, maybe you're not used to forward Euler and ODEs, and then that will be the more obvious way to go. Okay, it just depends on your comfort zone. Okay. So this is by far the easiest case study we have today. I translated my conclusion to Portuguese. Usei Google Translate, okay? But that's the point. The point is that it depends on what you're used to. Yeah. Okay. With this in mind, let's move on to something a little more complicated, which is the next case study. The stability of midpoint method, okay, so for stiff ODE systems. And so here is a system of ODEs. This F is not the same as before, it's a vector function. And numerical method for these differential equations, you take the time t and they dissect it, you know, and then at tk, the solution at tk is approximated by u sub k, and tk plus 1 minus dk is denoted by hk, the step size, and h will be the maximum. We will have this notation throughout today's talk. And the midpoint method is a discretization of this differential system, which reads uk plus 1 minus uk over hk, for that, is equal to f at the midpoint, average between uk and uk plus 1. And this is a well-known method. It is implicit, but other than that, it is simple. It is symmetric, looks the same if you take it minus t, integrate in minus t. Conservative method is symplectic. Astable and algebraically stable is second order, okay, as people have been looking at it for a long time. So now it has different uses, but I will concentrate on the use for stiff initial value ODEs. Okay, so what is stiffness? Stiffness is when you have in your given ODE system more than one time scale. Okay, so you have a slow scale and a fast scale. For example, you have some apparatus and it consists of mechanical parts and electrical parts. The electrical parts obviously move much faster, but the whole apparatus moves like the mechanical parts. And so you want a time step h that will resolve the slow scale, the mechanical motion, but doesn't have to resolve the fast scale. That's the point of a stiff problem. Okay, if you resolve the fast scale, then you may have a very small step size, and it will be an inefficient method. So let's now look at this discrete. So now let's assume that we start here, the discrete midpoint method, and now we ask, what is the continuous limit? Okay, and at first you will think the answer is really obvious. The answer is where we came from, right? I mean, shouldn't the continuous limit of this be this? Okay, and the answer is surprisingly no, because to get from here to here, you are looking at h going to 0. Where you're looking at h going to 0, you will have all the scales resolved when h is small enough. So that's not a stiff case. A stiff case is when h is not going to 0 in some sense. It will go to 0, but faster than any scale. Whereas here, we're looking at a case where you have some scales, some frequencies in the problem that one of the frequency is in fact smaller than the h that we choose. Okay, so this is not the continuous limit for our purpose. So now let's linearize f and call the linearization omega a, where omega a depends on time. Yeah? A is normalized to have order 1 norm, and omega is a coefficient which is very large. Okay, and now we discretize this by midpoint. This is a special case of f, but depends on omega. Okay. But now we are going to look at the stiff limit. So we are going to send hk to 0, but we are going to send omega to infinity at the same time, you see. And in this way, we are going to look at both hk going to 0 and it's not going to resolve all the modes. Okay. This is actually very, very well known. This is just singular perturbation limit. So the point is, of course, that now if we look at this, then you now have what does it mean omega to 0? I'm going to look at the family of problems and discretizations. Okay, so I want to somehow be able to analyze this. So here's a trick from 1972. Now, I'm not sure how many people in the audience were born before 72, but Heinz Otto Kreis, a great mathematician, came up with this very nice idea, in my opinion. And he said this, take your UK and multiply it by -1 to the power k, call it V. So Vk plus 1 will be minus k to the power -1 to the power k plus 1, UK plus 1. Yeah. So the for stability, I can look at V instead of U because VKs and UKs have the same magnitude. Okay. But the problem changes. If I now substitute what was UK, I call it now VK with a -1 and cancel the -1 to the power k. Then here we had minus for U, now we have plus for V. Yeah? And here we had plus for U, and now we have minus for V. And it sucks the oscillation that midpoint has out of the equation. And so now what we're going to do, we still want to send h to 0, but now we're going to look at an array of h going to 0 and omega going to infinity such that this gamma, omega h square over 4, is fixed. Let's say it's 1, for example. Okay, so no gamma. Okay, but we are going to keep h going to 0 and omega to infinity in such a way that gamma remains 1. Okay. And so now from here, so this is going to look like V, and this is going to look like the dV/dt. Yeah. So we just do some change of sides and so on, beautifying it, and you obtain the derivative here and the V here, and gamma inverse and A inverse. It's just algebra to make it look more beautiful. And now you see, now I can finally let h go to 0. The limit to 0 now is smooth. Until now, it was not smooth. It was rough. Okay, now it's smooth. And so I let h go to 0, and it's going to be dV/dt equal to my gamma inverse A inverse V. And this is a different ODE, a ghost ODE. And now you see the stability depends on the well-posedness of this initial value ODE. And usually, if the original is well-posed, this will be well-posed. If A is constant, for example, A stability says that it will be well-posed. But if A it depends on T, and it's a matrix depends on T, then it's not always the case. And so you see there are situations in which the midpoint method is not stable for safe problems in case that this ghost ODE is not stable. And that's a non-trivial result. And it's a theorem that I didn't bother to write as a theorem. But there are some rare counterexamples, and in the 1980s, I specialized in coming up with such examples. Okay, so we have actually two conclusions here. First, just because the differential equation is plausible continuous limit does not mean that it is adequate for your given task. It depends on the task. And then a good continuous limit, that's a good news, can be used to prove interesting theoretical results of practical importance. And that's what we achieve with this relatively simple example. Demonstration of both of these conclusions. Here is a third and more involved case study. Chaotic gradient descent and heat equation. So let's start with the simplest heat equation. U is temperature, du dt is equal to Laplacian u plus 1. And so this is actually 3 independent variables already. Homogeneous directly boundary conditions, and therefore we know that there is a steady state that satisfies this. It will be 0 in steady state. It satisfies that Laplacian u plus 1 is 0. And that is the model Poisson problem. Okay, and our goal is to integrate to steady state. We don't want to integrate the temperature at any time in between, but just to integrate to steady state through the parabolic PDE. That's the goal. And so now we can once again apply forward Euler on this problem directly. Okay, so we haven't discretized in space, just in time. And once we do that, we get this familiar structure. But this is unconditionally unstable. And whatever HK you take, step size you take, it is going to be unstable because functional analysts will say because this forward Euler operator is unbounded. Okay. Others will say you keep on differentiating here. It is not, cannot be stable for any positive HK. So that's the continuous. What is the discrete? The discrete consists of discretizing first in space and then in time. Okay, so we discretize first in space, so we put a mesh on this square. It doesn't look like a square, and here psi is the distance between adjacent points here, and our u is going to sit on those mesh points. Okay, and now we use a 5-point difference scheme to, so at here, it will depend on points here, 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 and here, to discretize the Laplacian. Okay, and so we're going to get a system that looks like du dt equal to minus au plus b, where u are the unknowns on this mesh organized by row or by columns. And A is symmetric positive definite, and it has only 5 diagonals that are non-zero. This is elementary numerical analysis stuff here. If you haven't taken the course, then just believe me that this is true. Okay, so we have this, and we have this one. This ODE we have seen before, of course. So we can look at the forward Euler here. Okay, and then we ask what happens to the stability. And in the first case study, we already know how to find the limit on this HK. This is what the first case study talked about. So we look at the eigenvalues of A and find that H must be a quarter bounded by a quarter psi square. I mean, sorry, that way around. If H is bounded by a quarter psi square, then the scheme is stable. And what is the connection to the continuous limit? The continuous limit says, okay, well, if psi goes to 0, okay, as the distance here goes smaller and smaller on the way to the Laplacian, then H will go to 0 like square of psi. So the continuous limit describes this, is a good limit for this discrete case. But is this stability limit necessary even if we allow hk to vary? This is the question I want to concentrate on. Suppose I can take some hk large and h small. Will that be, would it still go to 0 when psi goes to 0? And many people would say yes, but it's not true. The answer is no. You can have a large step for, you know, a large step will do a good job on the low mode of the residual, but then it will increase the large modes and the large eigenvalues and the amplitudes of the modes of the large eigenvalues. But if you then follow it by a few small steps, then it will decrease those, and you may still have it. It's possible to make it work. This is possible to do for parabolic problems, not hyperbolic ones, by the way. And this, the semi-continuous limit does not see. You see, so this is an example. Remember, in the beginning we said that you have to be careful that your continuous limit would actually see everything that goes on in the discrete level. That's the case where it doesn't. Okay, this sort of possibility. So you may say, okay, well, this is just words in the air. Show me that in fact this actually does something good for me. So for this purpose, let me once again switch. We have done it before, between the ODE with forward Euler and optimization with gradient descent. So once again, so for this I need to change the notation from U to X and from the step size HK to the step size alpha K, just because this is the usual notation. And so here is the forward Euler method, that is like we had before, exactly like we had before. Okay, and now the question is, which step sizes shall we choose for gradient descent? Okay, and so this choice is the greedy choice. Basically, it says minimize f along the direction r sub k. And this was Cauchy in around 1850, in fact, came up with this one. People call it steepest descent for some reason. And then Barzilai and Borwein in 88 said, no, don't do k, do k minus 1 here, which is counterintuitive, really. So let's call it lagged steepest descent. And so it's a two-step method, but it is still gradient descent. Okay, and that in fact gives you a convergent and chaotic method. So let's apply the LSD method for our integration to find the Poisson problem solution using the heat equation. Okay, so again, we discretize in space with the uniform step size psi. Okay, and now apply LSD time steps and stop with this topic criterion. So here's the size. I did it for different meshes with different size, and here's the maximum H's with this LSD method. You can see that as psi decreases, H certainly does not decrease like psi square. In fact, it does not decrease at all. You can have larger numbers here if we continue with taking psi smaller. Okay. So something here happens here that really the continuous model would not predict. And what happens, of course, is every once in a while you get a large step. So the blue here is the limit on stability, okay, for a constant step size. So if you take a small step here, small steps here, you can take a large step here, 1,000 times larger than the limit in this case. And then you can compensate for that with small step sizes. And you get a convergent method. it is not monotonically convergent. It jumps ups and down, and that is a problem, of course. But you can make it look less jumpy in a very simple way. Suppose that here you want to report the result. So what you do is you keep track on what has been the best results until now, and that's what you will report. Okay, so this is I will call it monotonizing MSD. We will keep L of K being the argument of Rj. Of course, we don't do it like that. We keep as we go along. We keep we keep track of who is L, and then from that we use from L K minus 1 we calculate L. So now we have a method that we can compare to other methods that are also the iterates of all these methods are in a Kirillov subspace, the same Kirillov subspace. It is well known that conjugate gradient is the best method in the subspace. Steepest descent, this is accelerated steepest descent, Nesterov method, and LSD. Okay, so let's look at the results. So we have already said that conjugate gradient method is best. There it is, but it's not interesting in this context because it does not generalize nicely to nonlinear, to non-quadratic objective functions. This is steepest descent. Now you can see why people hate it. The same thing will obtain with a good step size, fixed step size with gradient descent. Nesterov, in fact, show that this method is slower in theory than his method, which here I chose with good parameters, and that gives you this sort of result. Okay, so the iteration, the residual, and in this case the function error, get much faster down than the gradient descent, and here is this lagged gradient descent. So that is a surprise for many people, that in fact the accelerated gradient descent and this lagged gradient descent, at least for the quadratic problem, have similar performance. So these surprising computations demonstrate a case where the differential equation limit misses interesting action at the discrete level. This is, I want to mention one more case study, not completely, just mention it, not because it is not in the paper that I mentioned in the beginning, but it was the motivation for the paper that I never said aloud. The reason why I'm sort of starting to mumble is because this case study doesn't have a counterpoint in some way. So, but it was my motivation. So once again, you look at gradient descent, which is the method that people use for deep learning nowadays. So I shouldn't say that. They use stochastic gradient methods. Yeah, but many people study gradient descent because of this and how it can be improved. And so here is Nesterov method, the one that I mentioned before, with a particular careful choice of this alpha k. And it can perform faster. I will not say more, but there's been a lot of work trying to improve this method, in fact. So this is a two-step method because there's this extrapolation step here based on the previous xk minus 1. So people said, why don't we look at second order ODE limits? Okay. Now, the problem with this, I think I'm back here. The problem with this is, here's even easier to see in Pollack's old method, is that you need to let the alpha k and even beta k go to 0 in order to sort of say this is actually a discretization of the differential equation. So the motivation for looking at the differential equation was this sort of limit, but this limit is not smooth. You see, I mean, if there's one thing we know in optimization is the step sizes. These step sizes make a huge difference in practice, and suddenly we don't even look at them anymore, and that's a very big jump. So the limit of the alpha to 0, of the step size alpha to 0, is not a smooth limit, quotes. I don't want to define smooth here, but I hope you understand what I mean. Just like it was in the singular perturbation case, you sort of jump over information in some way that is not holy. Nonetheless, the people who have done it, here are the two kind of papers that many like dozens of other papers followed them. And I'm not sure if you recognize the names, but Boyd, Candace, and Jordan are all superstars, not just stars. And the connotation was machine learning. They're trying to study this because of machine learning implementations. I should say more specifically deep learning implementations. But there still is that problem. I mean, why are you allowed? Why do you think that doing something beautiful for this ODE is going to give you something beautiful also for the discretization, for the discretization in the context of optimization? That's not obvious. And in fact, we, being myself and other people, I am an expert on numerical ODEs. And I talked with other experts, and none of us understand just what's the point in some way. I should say that these papers did some beautiful work on ODEs, okay? But I do not see the connection to the problem that gave rise to this, namely accelerated gradient descent. So I don't see a smooth limit process here. What can be done is you can look at the ODE. This is what Pollack did back in '64. You can look at the ODE and design it in some way and say, oh, this is what I should strive for when I design accelerated gradient descent. That you can do, but there's a jump. I mean, what you can learn from this is qualitative, not quantitative, in my opinion. So I worked last summer with an undergraduate student on this, and he did lots of computations and deciphered the non-trivial paper here by these people here, but we couldn't get anything to really perform significantly better than Nesterov method. So I have to be careful here. I wanted to just, in conclusion, show once again the two slides I started with, because I know there's also material passed by here quickly. So there are great reasons to want to look at continuous limits, and I am encouraging you to look at that. I'm certainly not discouraging looking at continuous limits. You can get phenomenological understanding, and you can get efficient numerical methods. In the case of Navier-Stokes, there's no reason to look at anything else. Usually, not always, but usually, turbulence is accepted. And at the same time, you have to concentrate on the task you give, especially if you write a paper and say this is why we're doing it, and distinguish between qualitative information and quantitative information. That can be a big difference. And with this, I'm done. Thank you very much. Obrigado.
Hi, Uri. Okay, thank you. So we have a lot of time for questions. You had 50 minutes. You used only 40 minutes. So.
Oh. More.
Oh, if you want to, you still have 10 minutes. So it's up to you. So far, we have no questions. Maybe you can.
I can show you another case study if you want.
Okay, and while you do this, eu peço aos participantes, então, que encaminhem suas perguntas aqui pelo chat, que conforme elas forem chegando, eu vou encaminhando elas ao palestrante, tá bom? Muito obrigado. Please, Uri, go ahead.
So let me see this. I'm not destroying this one. Yes. So this is close to you, Antonio, and to other people in the department too. Professor Vinicio, Fabio. So here's a classical setup. You have a forward problem phi, and you're looking for a u such that and you have data d, and you want to look at the data fitting term here, and you add Tikhonov type regularization, like this. And now we're going to concentrate only on cases where U is an image or some discrete structure, not not conductivity of some differential equation. That all of my arguments here are only with the case when U is discrete. And then I ask, what do you do when you look at grad U? Because you are kind of assuming that U is continuous when you do that. So you have a limit here going to continuous, and then you discretize again. And and here you can have this row. You can have grad U square or grad U. So and we wrote I mentioned that's a huge number of papers on this. I mentioned only our work because we wrote the code based on this. Okay. And what did I do? So in numerical computation, almost everyone uses this paradigm, but in image processing, specialists in image processing rarely use it. Okay, and so there's already in the early 2000s we had this code I just mentioned, and we said, well, let's teach them. Let's use this code in order to obtain good results in the context of image processing. And I don't mean simply denoising an image, which is not an interesting problem. On the other hand, then denoising a three-dimensional structure is interesting. So we tried here and we tried here. Another imaging in 3 dimensions, this one we tried, and we tried on each of those. We tried the code that implements a better version of total variation, and all of them were beaten by discrete methods, completely discrete methods. And if you think about it, you can begin to see why. For example, here, I mean, when you have noise, this is an underlying triangular mesh. And so what you want to do is to find at each point the normal direction and the noise in the normal direction. Okay. For images, it will be bilateral filtering, for instance. But to find this, the normal here, you look at the neighboring points. This is how you find the normal. Whereas what we did before here, what did I do? We haven't seen any of that. Okay, what we did before is we take an integral over the entire domain, whereas the algorithm that worked, in fact, looks locally at each point. And when you looks locally at each point, you actually also you will obtain a very efficient algorithm, optimally efficient or optimal complexity, instead of solving some Laplace-Beltrami equation on this. Okay, so this was also a very fast algorithm that produced these results. The point here is being that the curls and also the eye details and this details, they are all reconstructed despite the noise. Okay, I will not mention all the other ones, but the point is that it's just the case that you have to be a little careful. When do you use this? The advantage is you can have more solid theoretical backing, and I think this is why our numerical analyst friends are doing it. But the disadvantage is that it can be outperformed in practice by brute force techniques. Okay, this is so especially if the phi is simple. The phi is the forward operator phi of u, and it corresponds to some local operation. You see, and if the data D is of high quality, Like, for example, what happens when you take a picture with your cell phone, and doesn't necessarily happen when you do some limited angle tomography. Yeah. So there is sort of orientation is different, and orientation of the practical people who work in industry would be to look at those continuous methods only when they have to, when the data is not good enough to produce good results. That's it. So that is my additional case study. Thank you. Have I filled the time, Antonio?
Yes, please. 4 more minutes if you want to.
No, I'm done.
Okay. So we have some questions here. I have some questions myself, but I start with the audience. So, Alex is here. O professor Alexandre Madureira está aqui presente, assistindo. Aliás, o professor Alexandre Madureira deve apresentar uma palestra daqui a 15 dias. E ele pergunta, Uri, nice talk. Would you say that the case of a golf ball relates to that? The golf ball is rough, and you can't play golf with a smooth ball.
I'm sorry. You play golf with a smooth ball?
No, you can't play golf with a smooth ball because it doesn't go far. The question is whether the case of a golf ball relates to that.
I cannot answer this question offhand. I need to think about it more.
Não apenas em bolas de golfe, mas nos trens-bala também. Hoje em dia eles fazem o trem-bala com a frente, com o perfil da bola de golfe, né? Para ele ter melhor penetração aerodinâmica.
Então, Alex, você está dizendo que a non-smooth surface ela stabilizes the ball, I think you're saying.
Yes. Okay. Sim, isso.
Yeah. I don't think it directly. I don't know, but I do not think that it directly relates. It's just a design that allows that increases the friction, of the air. I think, but this is. I'm on YouTube. I'm not going to go into this.
He's claiming that this happens with tennis ball. So, because, as I understand, the smooth golf ball is the asymptotic limit of the usual golf ball.
I see what you're saying. So what Alexander is saying is that if I take the limit too quickly, then I'm losing an important physical or engineering design.
Yes.
Yeah.
I think this is the question.
Yeah, that's actually a cool question.
Mm-hmm. I see. Okay. I have a question myself. So far, only Alex sent a question. Let's wait a bit more. But you mentioned, você falou sobre deep learning e machine learning. Qual exatamente a diferença de deep learning e machine learning? E quais são os algoritmos que são usados na área de identificação de parâmetros, né, para machine learning?
Okay. Deep learning is a subset of machine learning, but it is a very major subset. Yeah. Mm-hmm. So machine learning is basically says that you want to design programs that learn, that adapt, and learn while they're running. Yeah. And whereas the normal programs we use, for example, for inverse problems, is you have the program and it just produces results. This one also learns. So this is machine learning. There are methods in machine learning that are not deep learning. Deep learning is neural nets. Yeah, you use neural nets, and so you have layers. And the deep is when you have many layers. Yes. And yeah. So some people say that nowadays everything is done by everything is machine learning is done by deep learning. But I think that people have started to sort of back out of that a bit in recent times, because you need a lot of data for deep learning to make sense. Yes. And you don't always have lots of sufficiently good data. So in those cases, people try to introduce information or modeling information. Although they are nowadays they're trying to be a bit more careful than just throwing in a differential equation there. So they're trying to do better. For example, there's lots of work on using discrete Laplacian and so on.
Yeah, sim. Mas o interesse maior em Deep Learning é você modelar a rede propriamente ou você resolver o problema de identificação de parâmetros?
Please translate this.
Okay. So, what is the most important task in deep learning? The modeling of the network itself or the parameter identification problem? Parameter identification is an optimization problem.
No, okay. So
algorithms.
Yeah. So that is actually an important point that many people miss. In deep learning, usually the importance of the recovering what we usually recover in inverse problems is not the goal. The goal is to use data in order to produce better data, so to speak. Yeah. So I call it simulation. You look when you're done, you're looking at simulation results. And so in the usual the way we look at, for example, inverse problems, it is not the conductivity that matters. It can be in big error. What matters is the solution that we obtain conductivity. Yeah. So you train the network that you're constructing, and then what you measure is simulations, which you also you use in order to do classification. Yeah. So at the end, you have labels and you sort of jump to the nearest label. But it is all the data you see is never the parameter of the inverse problem. It's always the simulation results.
You say you try to solve a problem that you don't know the solution. This is a very hard problem to solve. But then you're saying that the identification problem, the training of the network is the most important issue related to deep learning so far.
Yeah, the training is the closest to the training part of deep learning is indeed where you could imagine introducing some knowledge in order to solve for example, parameter identification. But again, what is interesting in the end is not the parameter identification,
no,
but
of course,
the results you get with it. Yeah.
Yes.
That's actually a big difference in computer graphics, for example.
Yes, of course. Yeah.
You look very stupid. Sometimes, I have, in fact, a paper together with many other people where we were solving inverse problem in the context of soft deformable body simulation, and we would look really stupid if we showed the parameter identification, but the results look very good compared to reality, and to compare very well to realistic experiments.
Okay, so thank you, Uri. So no new questions. I think the audience is satisfied with your presentation, and since they have no more questions to ask, então eu gostaria de agradecer a todos pela participação na nossa palestra, web palestra agora do colóquio do Departamento de Matemática da UFSC. Agradecer ao professor Uri pela excelente palestra e desejar a vocês uma boa semana. Nos vemos na próxima sexta-feira. Nas duas próximas sextas-feiras teremos palestras de 2 professores do LNCC de Petrópolis. Um deles está assistindo aqui, o professor Alexandre, e o outro, o professor André, que vem na próxima sexta-feira. Então, muito obrigado a todos. Agradeço pela participação. Vamos encerrando aqui a transmissão de hoje. Um abraço.
Tchau.
Let's see.